Hello there, and welcome to another episode. So, we are following up from the previous episode where we spoke about interrupt requests, interrupt service routines, and the vector table. I mentioned the vector table in passing, and I promised you that I was going to dedicate an entire episode to discussing what the vector table is and how your microcontroller boots up, so that you have at least a good picture in your mind when it comes to having an understanding of how everything fits together on your microcontroller unit. And that is precisely what I'm going to do in this video. So let's start off by asking ourselves, how does the microcontroller even start executing the code that you write in main, right? The reason this question is important is if you have programmed for a long time, and of course it doesn't even have to be a long time, but you know that whenever you define a function, that function has to be called, and it is in the invocation or the calling of this function that actually gets the function to do what it has to do, or that gets the processor to execute the specific instructions that you have written in the function. If you were programming for an environment that had an operating system, you already know by now, most likely, that the operating system has something called the program loader, which loads your program instructions into memory and starts executing your main function, right? But here we are programming for a microcontroller unit that most likely or most often has no operating system. So the question is, who or what does the calling of the main function that basically gets your firmware to do what you have set out to build it to do? All right, and this is a very good question that you have to ask if you are an inquisitive learner who always wants to get beneath the details to see how things fit together. It's a very good thing and a very good behavior to have. So that is a question we are going to ask ourselves. We start off by writing int main void, and then we spill out our code in here. And the question again is, what is invoking this main function? Because we don't call it manually anywhere, right? Now, when we generated this project with STM32 Cube IDE, I started by deleting what was in main. I did that just to prove to you that all that CubeMX is doing is to generate code for you, and I basically hate it. I don't like code generators and stuff. I think they get in the way of understanding. So we just deleted the code that was written in there. If I come right now and I make changes to this IOC file, it's loading. One of the things I hate, the slowness, right? So if I come and I make changes in the IOC file and I save the changes, it's basically going to overwrite every code I have in here and generate code that reflects the changes that I made in the IOC. God, this thing is slow. Not like it even matters in this video. I'm not going to use it for anything. I was just opening it for you to see you can make some changes and it's going to generate code, but it's too slow. I don't like it. We don't have time for it. So no, don't generate any code. Switch to C++ perspective. Okay, so now let's go back to answering the question, what calls our main function? And like I said, when CubeMX or STM32 IDE generated the project for you, there is this folder called startup, and inside it there is this .s file. .s basically it means it's an assembly code. So we can double click on this file and then we see some assembly code in here. Don't be scared by what you see so far. It's pretty simple for you to understand, not because you understand assembly, but I'm going to try my best to explain it to you. First and foremost, I need you to note that this doesn't necessarily have to be written in assembly. Personally, I have written the same startup code in C and it worked perfectly fine. I do not see an advantage to doing it in assembly, but again, this is a code IDE generated for you and they chose to write it in assembly, which is fine. Now, this startup code, even though it's written in assembly, it is compiled together with every other code that you write in C, and that is how you get your final ELF or binary file that you flash onto the microcontroller. And don't be surprised that the IDE is kind of mixing assembly code together with C code. The truth is, even the C code you write here actually gets converted into assembly code, and then the assembler takes the assembly code and converts it to binary, which you send to the microcontroller for execution. It is not transparent, but there are flags that you can set. So there are things we can do to actually see the assembly code that is generated for this, but I'm reserving all that for when we start doing actual bare metal programming. So back to the startup file here. It's written in assembly, so I'm not going to bother you so much, but I'm going to give you a brief theory of what actually happens when your microcontroller unit boots up. So when your microcontroller unit boots up, and in this case it happens in two instances. The first instance is when you connect the power supply to your dev board. The moment the microcontroller unit begins to receive the requisite level of voltage across the appropriate pins, it gets into what is known as the reset mode. Another way to put it in reset mode is by pressing the reset button on the board. So these are the two ways by which you can put it in reset mode. Now, once reset happens, something else happens before this function here called reset handler begins to execute. So in actual fact, the true beginning of your program is the reset handler. It doesn't matter that you didn't write it by hand. By design of the microcontroller, it starts executing from the reset handler, and we'll go to the reference manual to confirm. Okay, now I said that something else happens before this reset handler executes. What happens is that there is a ROM, okay, a read-only memory inside your microcontroller unit that has some factory flashed program. Okay, you can call it a bootloader for the lack of a better word. What this program that is loaded onto your microcontroller unit, so whether you have a board, a dev board, or you buy just the microcontroller chip, it doesn't matter. That program is loaded onto the microcontroller chip by ST or whoever is your semiconductor manufacturer before they sell the chip to you. Now, what this code in the ROM does is it looks at some pins on your GPIO. So usually they label them boot 0 and boot 1. I wish this guy would load faster than we could see, but not important now. So there's on boot 0, boot 1, and then depending on whether one of them is high and low, the combination of high and lows on those pins, the ROM is going to determine where to boot from. It can boot from the flash. So your microcontroller unit has a flash memory, right? On mine, the STM32 F303, which is on the discovery board, has 256 kilobytes of flash memory and I believe 64 kilobytes of SRAM. So even though these are two separate physical memories, they share the same address space. That is another topic for another time. But the flash memory is reserved for your program instructions. So when we write code and we compile and we flash it onto the microcontroller, the binary that represents the code we've written actually gets written to the flash memory. So the ROM, depending on the configuration of boot 0, boot 1, is going to determine, okay, I'm going to boot from the flash. Or it can also say, I'm going to boot from in a mode that prepares the board for code upload, and that is what happens when we click this button here. Basically, the code behind this sets your board into bootloader mode or flashing mode. So it means the ROM starts and then it says, okay, I'm not going to boot from flash. I'm going to prepare myself so that binary instructions which represent the program can be sent over UART, and I will write that to flash. So these are the two modes. Right now, let's focus on what happens when we are booting from flash. The first instruction that the microcontroller unit is by design made to execute is known as the reset handler. So if you see something like this, it's a name and basically a label, but you can it's equal to a function in C, but this is how you do it in assembly. So you see that there is a reset handler and a whole lot of stuff that is going on here, which I'm not going to explain to you. But the most important thing is at the latter part of this function, okay, at the latter part of reset handler, you can see BL main. BL is basically a branch instruction. So it's telling your microcontroller to branch to a particular memory location where the main function is stored. So this is why I said the reset handler is actually what begins executing, and after it is done, it calls your main function. So that answers the first question we started with, that who or what is responsible for invoking this main function. It is happening here because this assembly code executes first, and when it is done doing what it has to do, it calls your main function. Even though when we start doing bare metal programming, we will write this startup code from scratch in C, and I'm going to explain everything. Let me try to explain to you. You get a picture. So when you write your program like this, there are some data, for example, constants that you declare. Those ones goes, they get written to flash memory, but data that you actually manipulate, data that you read and write in your program also has to go into the SRAM. That is why I said your microcontroller unit has at least two physical memories, the flash and the SRAM. The SRAM is for runtime manipulation of data. So this code here is basically setting up the runtime environment. It's preparing the memory and loading certain data in your program that needs to be manipulated from the flash into your memory, and it also set up the stack pointer. So what your program is going to use as a stack, so that when functions are called, it's going to load what is known as stack frame and stuff onto the stack, right? But the most important thing is after it is done doing that preparatory steps, it calls your main function. So then whatever you wrote here begins to execute. Like I said, even your code in C gets converted to assembly before getting to binary. So it doesn't matter that they have written the startup code in assembly, we can do the same thing in C. All right. So in the startup code, apart from this, you can see that we have something called GPFN vectors. This is the vector table that I spoke to you about, and what the vector table represents is just memory addresses of functions. You might ask yourself again, why is this important? It is important that the processor knows specific addresses where particular functions have been stored. This is what helps it to be able to respond to interrupts, as we saw in the previous video. Now let's go to the reference manual, and then we will see one-to-one mapping between the reference manual and what we see in this code here. So I still have the reference manual opened. Just go to the NVIC section. So when you open the interrupt and event section from your reference manual, you can see that it has interrupt and exception vectors. Okay, so it says the table is the vector table for STM32 F3 blah blah blah, is a vector table for blah blah blah. So basically you see that each vector or each function has what is known as a priority, and it has a type of priority. It has an acronym, it has a description, and a specific address where it has to be stored. So this one, for example, is called reset. By the way, the very first item in your vector table is the stack pointer. That is why when you come here, you see the first thing here is e-stack. This thing is working together with what is known as the I don't know why I've forgotten the linker script. Yeah, so this is the linker script, and this is also something we'll get into. But like I said, my flash is 256, okay, and my RAM is 40 kilobyte, and there is some other CCRM. This is a RAM that is very close to the processor for fast access, and that is 8 kilobytes. So this is a definition of the memory layout of my microcontroller unit. In this particular case, it's not so important, but I just digressed so that you'll understand what's going on here. But basically, the E stack, if I search for E stack here, so underscore E stack, yeah, you see. So E stack is basically putting it at the end of the RAM. So the very last address of the RAM is where your stack begins, and your assembly code is able to read that from the linker script and set it as the first word. So this vector table is an array, and the first word of it is the stack pointer, and then the very next thing is the reset handler. Let's go to see, this is the reset. Now look at the priorities here. This is -3, -2, -1, 0, 1, 2. The other surprising thing you want to note is that when it comes to priorities, the smaller the priority, the higher the priority. You have to remember this. So -3 means it is of topmost priority. And then after it comes NMI. NMI means non-maskable interrupt. This is an interrupt that cannot be turned off because it is super important. After reset handler, this is the most important handler. It is called NMI, and the RCC clock security is linked to the NMI vector. Basically what this handler does is, when the system boots up and there is any failure to the system clock, imagine a microcontroller unit without its clock is useless, and so this interrupt handler kicks in. So in the code that represent this interrupt handler, some of the things you can do is maybe to switch the clock source, which are all things that we talk about. There is too many chicken and egg problem in microcontroller programming or firmware design, so I always keep saying we're going to talk about it. I just want to give you enough information, and then when the time comes, we will talk about the details. You see that after NMI there is hard fault. Let's see. So there is hard fault, and then there is mem manage handler. Let's confirm. There's mem manage. There's bus fault. Let's confirm. There's bus fault. Now if some handler is indicated as reserved in the reference manual, then it is set to 0 in the code base. Right now, what is the vector table? I want you to imagine the vector table as your phone book or your contact list on your mobile phone, right? You are basically storing phone numbers against names, and then anytime you want to call somebody, even though you search for their name, what you are actually after is the phone number. So you dial, and then the phone gets the person gets a call and answers you, and you are able to talk. It's a similar thing. This is a very vague presentation, but it helps you to get an idea. It is just addresses of actual functions that are either defined or you will define them later. But it is so important that these are all already defined as weak functions. A weak function is basically a function that has a default implementation, but you can overwrite it by creating another function with the same name, and what you create overwrites the weak version. That is how come when we wanted to handle ESTI0, when we wanted to implement interrupt request handler on pin 0 for the button in the previous episode, we had to overwrite this function here. And I told you that the name ESTI0 IRQ handler was only special because that is how it has been named here. If I named it button IRQ handler, I would just come into this code here and also change it to button IRQ handler. I compile it and it is going to work. So I know this can be a bit too much for you to take in, but it still helps you to understand the boot up process of your microcontroller unit. You also get to understand why this startup file is here, and going forward you won't be too afraid of it. Like, you can look at it, even though you are not an assembly programmer, you can look at it and sort of have an idea what is happening. So you see that it is defined as weak. That is what I told you. So all the functions are defined as weak. What it means is that you can overwrite them. So let me look for the weak definition of STI0 handler. So this is it here. So it is defined as weak, and that is why we were able to re-implement it here. Now let's see what happens for some of the default or most important handlers. So if we come to src, I see there's a file here that has underscore it.c in it, and I told you that this is also generated by STM32 IDE. The idea behind it, I like it anyway, is to sort of let you separate out all your interrupt service request handlers in their own file, not to mix them up like we did here. So like I said, I could just copy this code and then paste it here, anywhere here that makes sense, and it's still going to compile. Now let's see what the default handlers for the most important interrupts are doing. They basically just set the processor in an infinite loop, so they let the processor hang. In other programming languages you call it a panic. So NMI, for example, this is non-maskable. It means you can't turn it off. It is on by default and there's nothing anybody can do about it. Now when the processor boots and it does the reset handler and it checks whether the clocking system on the microcontroller unit isn't working. A microcontroller unit without clock is a useless piece of hardware, so then it just hijacks the processor. It's like an infinite loop that is not doing anything, but it's not giving the processor the opportunity to even do anything. Meanwhile, in your own firmware implementation, if you have plans or if you have strategies in place to recover from some of these problems, you are free to implement them in this code here. So let's say if I want to check if let's say my clock is not working, the microcontroller unit has multiple clock sources, so I can switch to the next available clock source that works. I will see if in the next episode we can intentionally trigger some of these handlers to see how they behave. I know this has been a long video. I like to keep my videos short, but I tried my best and this is what I could do. Thank you very much for watching. Those of you who haven't subscribed to the YouTube channel, if you're watching this on YouTube, please do me a favor by subscribing to the channel to help it grow. Thank you very much for watching, and I will see you in the next video.